Let's look at a few different notations that represent the derivative. So these are symbols or things that could be written that are referencing either the first or second or third derivative or so on. And so in all of these cases, we're going to let y equal f of x be the original function. And for the first derivative, you have notations like y prime and f prime, and most people are familiar with that one. There is also a different notation that I love, and this is called Leibniz notation. I'm not going to quiz or test you on that name, but Leibniz is just another mathematician who did a lot for the development of calculus a long time ago. So that's Leibniz notation, and that's probably my favorite. The capital D with the subscript X is not one that I'm going to use, but if you happen to run into it, I thought that I might throw that in here. The reason I love Leibniz notation is because it really does look like the formula for slope, which is a change in y over a change in x. And if you look at his notation, he used a dy dx, and that literally is representing the change in y over change in x. So the derivative, which references slope, that dy dx notation screams slope to me. And I want to talk about the differences in those two notations. So the dy dx, that is a noun. So the dy dx is the noun saying the derivative is this. So if y is x cubed minus 4x, the derivative of y with respect to x, and that's how you read that, the derivative of y with respect to x, or dy dx, is 3x squared minus 4. So if you write dy dx, then that is representing the derivative. However, d dx is what I call a command, or you can think of it as an operator, and it is telling you to find the derivative of what follows. So here I have d dx right here. I have d dx parentheses x cubed minus 4x. That means find the derivative of x cubed minus 4x, and the answer is 3x squared minus 4. The dx notation is very similar, so I could write dx of x cubed, and the derivative of x cubed would be 3x squared. So that is also an operator, the capital D with the subscript x, but I'm not going to use that much. Another thing I like about Leibniz notation is that it is very obvious. This line right here, and right here are two different equations that mean the exact same thing. One of them has Leibniz notation and the other one has the y prime notation. And I like the Leibniz notation because the piece that represents the derivative is very obvious, ugly, loud, obnoxious, like my mother-in-law. And it's very hard to lose it. If you're using y prime notation, sometimes that y prime can kind of get mixed in with all the other y's and you have a hard time keeping them straight. So there's the first derivative notation. And now that you know the first derivative, the second derivative and on is a little bit easier to understand. So with the prime notations, you have y double prime, f double prime, so on and so forth. For the Leibniz and the operator type stuff, they actually use what looks to be an exponent of, here's where we have d squared y over dx squared, d squared over dx squared. That's simply referencing the second derivative. That is not the first derivative squared. That is the second derivative. Those exponents are in the correct spot. And it's the same thing with the d with the subscript x. If there is something that appears to be an exponent of 2, that's actually the second derivative, not the first derivative squared. And the third derivative is the same type trend. So y triple prime, f triple prime, and then the exponents of 3. And I'm using the word exponent loosely. It is an exponent, but it's really referencing the order of the derivative. So that would be a third derivative. And then finally, if we were to go on and do something like the 17th derivative, the Leibniz notation and this operator notation of d with the subscript x, those are pretty predictable. It's going to be d 17y over dx 17. D17 over dx17 for the command, find the 17th derivative, and then d with the subscript x and an exponent looking thing of 17. So those are predictable. That's another good thing about Leibniz notation is that it is consistent throughout all orders of derivatives and how you present it. But the prime notations get a little bit trickier because you don't want to do like y and then write 17 tick marks all the way down to the whatever. So instead of doing the tick marks, when you get to higher order derivatives with the prime notation, what they'll do is they'll put the order of the derivative in the place of an exponent with parentheses around it. So y with an exponent of 17 in parentheses means the 17th derivative. Same thing with f. F 17x, that means the 17th derivative. And do note that sometimes you will see something like f with a 5 like that. If there are not parentheses, that is actually the function f of x raised to the fifth power. It's not a derivative. So the parentheses are what's separating the exponent from the derivative. And this notation where they put the number in parentheses typically starts at the fourth derivative. So you usually won't see y with 4 tick marks. What you'll usually see is y with the 4 in parentheses, and that would indicate your fourth derivative. So there's a quick rundown of the different ways, probably the most common ways that you will see derivative representations. There are a few other ones out there, but these are the ones that you're going to encounter more frequently.